Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing Layer 2 security and loop prevention. In this lesson, we'll be covering forwarding loops, what they are, and how they affect a network. You may have heard stories of network administrators troubleshooting a broadcast storm. Whenever I hear these stories, they always sound like something very violent or eventful. When I think of a broadcast storm taking out a network, I think lightning and sparks. However, if you've ever had to troubleshoot a broadcast storm, you know that it doesn't actually cause your network devices to ignite or throw sparks. Although that would probably be helpful if they did in troubleshooting or investigating the source. In the following slides, we'll review what a loop is, why it's bad for a network, and review at a high level what we can do to prevent them. So let's get started. First things first, what is a forwarding loop? A loop occurs when a single broadcast domain is connected together such that a physical or logical loop is formed. When a frame is forwarded in this topology, a broadcast storm occurs. This phenomenon occurs because the layer 2 Ethernet header does not contain any fields which prevent it from being forwarded forever. Where the layer 3 IP header contains a TTL field, or time to live, allowing the packet to be forwarded through a maximum of 256 hops, the layer 2 Ethernet header has no such field. The layer 2 frame can be forwarded forever in a loop according to the Ethernet protocol. Broadcasts are of primary concern when considering the existence of a forwarding loop, because a switch uses the flooding mechanism by default to forward these frames. As shown in our diagram here, whenever each switch sees the broadcast frame, it will flood the frame out all interfaces in the same broadcast domain. However, network storms can be initiated by any frames which cause the switches to use the flooding mechanism. Recall that these are broadcasts, unknown unicasts, and multicasts. Although broadcasts are the most common of the frame types, if the network were to see a large influx of unknown unicast frames due to some misbehaving device or attack, then this too could also initiate a storm. See, every frame transmitted on a link uses up some of the link's available bandwidth. If enough frames are being forwarded in a loop, all available bandwidth will be utilized forwarding the looped broadcasts, with no bandwidth remaining for other unicast traffic that typically is used in production data streams. In addition to saturating links with unwanted traffic, storms are generally created by broadcast traffic, which is processed by the CPU of all attached nodes. This is because a broadcast frame is technically destined for all nodes in a broadcast domain, meaning all nodes which receive it should process the frame and inspect the payload. In the case of a Junos device with a rate limited link between the PFE and RE, a broadcast storm can prevent management access to the device due to the link between the PFE and RE being saturated from all the broadcast frames which need to be processed by the RE. So, now that we've firmly determined that broadcast storms are bad, let's review how to prevent them. The first way to prevent a loop is, well, to simply avoid connecting your network in a loop topology to begin with. There are multiple problems with this solution, though. First and foremost is that this method of prevention has no assurance. It's unreliable, and we can't be sure that we'll never accidentally connect our switches in a looped topology. The other primary issue is that we currently have no method to provide a highly available network which can automatically survive a link failure. In order to survive a link or device failure, an alternate path to the same destination must be available, which, by definition, would be a loop in our network. Spanning Tree Protocol, or STP, represents a family of protocols which are designed to create a loop free topology. As part of the JNCIS ENT, we're only reviewing the original 802.1d Spanning Tree Protocol and 802.1w Rapid Spanning Tree Protocol in depth. There are other flavors of Spanning Tree Protocol, like Multiple Spanning Tree Protocol and VLAN Spanning Tree Protocol, which are not covered by the JNCIS ENT. As you may notice here, STP and RSTP are rather old protocols, with the 802.1d standard originally being published in 1990, over 30 years ago. The most recent revision of the original 802.1d was published in 1998. A follow up overhaul to the protocol was published in 802.1w, entitled the Rapid Spanning Tree Protocol, originally published in 2001. The latest revision was published in 2004 with some amendments in 2007. In the next slides, we'll do a quick overview of the function that STP performs and some of the key terms to know when talking about the operation of Spanning Tree Protocol. To create a loop-free switching topology, at a high level, STP performs a four-step process. First, all switches in the network exchange Bridge Protocol Data Units, or BPDUs, which include information about what priority each switch has in reference to the root bridge, and the sum of costs of all links on the shortest path to the root bridge. See, the root bridge is the core of the LAN. As the name suggests, Spanning Tree Protocol creates a tree-like topology, where a single root node is at the center and arms, or branches, spread from which are unconnected between each other in a loop-free topology. Once all nodes in the LAN exchange BPDUs, all nodes then agree on which one is the root of the tree topology. This process of determining the root of the tree topology is called the root bridge election. Once the root bridge election is complete, STP assigns certain states and roles to each port in the topology. And once all port states and roles have been determined, the tree in STP is fully converged and in a steady state. Now that we have a high-level overview of how STP operates, let's take a look at some of the key terms we need to know to talk about STP. We have 5 terms here that we should know so we can go deeper into the flavors of STP. First, we have the BID, or Bridge ID. The Bridge ID is composed of the priority value and then the MAC address of the bridge, where the most significant number is to the left, and therefore would be the priority value. So the priority value will be the primary tiebreaker, while the MAC address will then be a secondary value to use. The bridge ID is used only in the root bridge election process. The lowest bridge ID wins the election. Since the priority value is the most significant digits of the BID, then the administrator can configure the definitive root bridge by manually configuring the bridge priority of the bridge which should be elected as the root. Since the bid is also made of the MAC address of the bridge, if identical bridge priorities exist on the network, then the switch with the lowest MAC address will win the root bridge election. Now, consider though that manufacturers generally manufacture devices and assign MAC addresses sequentially. So, older devices have lower MAC addresses. This means that if you do not choose and configure your root bridge intentionally, then your oldest and least powerful switch could end up winning the root bridge election. This is why it's very important to always choose your root bridge intentionally. Next up, we have the Bridge Protocol Data Unit, or BPDU. The BPDU is exchanged between STP speaking switches. The BPDU not only includes the bid, as we've been talking about, but also the priority value and ID value of the port it's being transmitted from, which is important as a discriminating factor in the topology calculation, as we'll see in a future lesson. The next term we'll want to be aware of is the port roles of designated ports and root ports. The root port is one which, in a converged STP topology, is in a forwarding state and is the lowest cost path between the local switch and the root bridge. A designated port is one which is in a forwarding state and are not root ports. These are downstream ports pointed away from the root bridge. Finally, we're looking at root bridge and designated bridge. We've already reviewed what the root bridge is, that it's the core of the network. Designated bridges are effectively all other switches in your network, which are not the root bridge. I appreciate you reviewing forwarding loops and the creation of a loop-free topology with me. In the following lessons in this course, we'll review the operations of STP and RSTP in much greater depth, showing why these protocols are generally avoided in modern networks in favor of faster converging protocols. I hope that this has been informative for you, and I'd like to thank you for viewing.